Hi, in the Gauss reduction method, I told you to put the coefficients we are using for the reduction instead of the zeros in the lower part of the matrix. In fact, I told you that these coefficients I will be using them later, and now it's the time to use them. Sometimes in some problems we have to solve a system Ax equal b, but we need to solve it many times for different values of b, because b depends on some given parameters in the problem. Okay, so if we want to do so with the Gauss reduction method, we have to do the method or perform the reduction at each time b is changing, because the reduction method will change as well. When we do the reduction, I recall we are performing it on the augmented matrix where we have a and b in a whole table that we are transforming to an echelon form. So it's interesting to find a method that allow us to solve the system Ax equal b, and that deals only with A and does not touch B. So in this case, if B is changed due to the change in the parameters of the problem, I can still use the same method or the same calculation I did, because these calculations were not depending on B. So this is what I want to introduce here, the LU decomposition. Okay. So as I say here, sometimes it's interesting to solve the system without modifying B. When we have to solve many systems with, here it's not same, it's a mistake, it's with different B. In this case, we use the LU decomposition. In fact, the idea is the following. If the matrix A can be written as a product of two matrices, L and U, where L is a lower triangular matrix and U is an upper triangular matrix. If A can be written as this product, then the system Ax equal B is equivalent to the system LU x equal B. And to solve the system LUx equal B, it's much easier than Ax equal B, because all we have to do is to solve two systems. The first one is Ly equals to B, where y is equal to ux. So we solve the system Ly equals to B, we find y, and then we inject it in here as a second or right hand side in this second system, and we solve ux equal y. And why these two systems are easier? Because L and U are both triangular forms, triangular matrices. So to solve a system with a triangular matrix is easy, because that's what we did in the reverse path method. So if we go back to the example that we did before, or an example we did before, if you go back and see, we did the reduction procedure and we obtained this augmented triangular system or triangular matrix, and we have placed the coefficients in squares. Okay, now I will define two matrices from this reduction. The first one is given by the coefficients in here and one on the diagonal of the matrix. So I will define this L is given by the coefficients with the one or ones placed on the diagonal. Okay, this is a lower triangular matrix, of course, and then I will define another one, which is U, which will be the upper triangular part of this matrix. Okay, so this is U and this is L, but I should add ones to the diagonal. So if I define these two matrices, I will remark that if I multiply L by U, I will obtain A. Let me consider, for example, the second example we did also. I obtained this augmented matrix. Okay, so all the same thing. I will take the coefficients to construct the lower part, and the upper triangular matrix to construct the upper part, so the matrix U. But of course, I will consider the coefficients in the order that in which they should be, because this was a method with pivoting. So I changed the place of the rows. So in here, this one will be the fourth row. This one will be the third row, and so on. Okay, and so I will obtain these two matrices, and I notice that if I multiply L by U, I will not obtain A, the A that we had in this example, but a slightly modified version of A. So I repeat, in the first example, when I constructed L and U, the multiplication tried to do with L times U gave me A. But in this second example, when I constructed L and U, the multiplication gave me a modified version of A, where the rows are modified according to the modifications that I did in the index vector. To write this down properly, I would say that in this case, LU is equal to PVIA. When I say PVI, is a matrix P that depends on VI, on the index vector. So it depends how we perform the pivoting, so the changes we did in the index vector will modify the matrix P. So the matrix P is a matrix that if I multiply it by A, it will give me the modified form I have in here. So how do we construct this matrix P? If Vi is given by this index vector of permutations I did, then the permutation matrix P corresponding to Vi is the identity matrix In modified with the same order. Let's understand it with the example. So in the example we did, we had Vi is equal to 2, 3, 1, 4. So we construct the matrix P according to this index vector. The first element is 2, so we'll start by E2, which is the canonical basis in R4. The second element of Vi is 3, so then we have E3, and then E1, and then E4. But we put these vectors in columns. So here we have E2, E3, E1, and E4. So this is E2, E3, E1, and E4. And so if we multiply this matrix times A, we'll obtain the modified version we had before. So LU is equal to this permutation matrix times A. We can sum up in the following theorem. So if A is a square matrix of nth order, L is a lower triangular matrix, U an upper triangular matrix, and Vi the index vector, then PVIA is equal to LU. Of course, PVI is equal to identity when we perform a Gauss reduction without pivoting. So writing now A as a product of a lower triangular matrix and an upper triangular matrix, A equal LU, will help us to do many applications. First, it will help us to solve the system AX equal B. Okay, I already explained how to do this by solving two systems, Ly equals to B and Ux equals to Y. So we'll see this in the example. If we have this matrix, then if we perform the decomposition, try it by yourself, you will obtain L as being this matrix and this is U. So now to solve the system, we say let Y be a vector given by y1, y2, y3, then Ly is equal to B means that we have this matrix times y1, y2, y3 equals to minus 2, minus 5, 0, and we can solve it by the reverse path method, starting by the first one because it's a lower triangular matrix. So we obtain y1, y2, and y3. Then we solve the system Ux equal y, where y is this right hand side term that we obtained earlier, and then we solve this system and we obtain the x, which is the solution to the system Ax equals to B. You can of course do the same with this second B as a practice example. The same work can be done when we have a Gauss elimination method with normalized pivoting, but instead of having Ax equal B equivalent to Lux equal B, now we have P A X equals PB. I mean, the system AX equal B. We will multiply it by P. We will obtain PAX equal PB. And then this is equivalent to LUX equal PB. So now we have to solve this system, which means that we have to solve two systems. Ly equals to PB, and then Ux equals to y. And we do the same these calculations in here. Try to practice it and do your own calculation. Of course, notice how we constructed the P as I explained before. Another application of the LU decomposition is the calculation of the determinant. In fact, if A is equal to LU, then the determinant of A is equal to the determinant of LU, which is equal to determinant to L times determinant of U. But the determinant of L is equal to 1 because L is a lower triangular matrix and its determinant is the product of the diagonal elements, which are 1. They are all equal to 1. So the product is 1. And then determinant of U is equal to the product of the diagonal terms UII. So the determinant of A can be calculated directly by multiplying all the diagonal elements of U. Even when we perform the Gauss reduction with pivoting and we obtain PA equals to LU, then the determinant of P times determinant of A equals the product UII, but determinant of P is nothing but y minus 1 power s, where s is the number of permutations. So if we do this calculation, we will obtain as well determinant of A as being minus 1 power s times product of UII. So this is another application of the LU decomposition. The third one is the calculation of the inverse of A minus 1. In fact, we know that A minus 1 is equal to IN, which means that if we multiply A by a matrix that I will write as follows, where C1, C2, and Cn are the columns of A minus 1, is equal to E1, E2, E3, where E1, E2, E3 are the canonical basis of Rn, which are also the columns of In. Okay. This means that if I multiply A by the first column in A minus 1, it will give me E1. The thing is that E1 is known, A is known, and I have to find C1. Now, writing LU instead of A, I will have LU C1 equals to E1, LU C2 equals to E2, etc. LU Cn equals to En. And each one of these systems, and I say system because, as I said, E1 is known and LU is known, and the variable now is the first column or the second or the nth column of A minus 1. To solve the system, I can proceed easily because we have already the LU decomposition, so L is lower and U is upper, so we solve two systems. Ly equals to E1 and U C1 equals to Y. And if I do so, I will obtain C1, which is the first column of A minus 1. Same thing, I will do the same thing for C2 and Cn, and this way I will find the inverse matrix of A. In fact, this method is very useful because the usual calculation of the inverse matrix is something very expensive in terms of computational time. And if we have a matrix A with the LU decomposition, it's much easier to perform this method to calculate A minus 1. Now, if we have the LU decomposition that we obtained by a Gauss reduction method with pivoting, then instead of the identity we have P, I mean, we know that LU is equal to PA which means that LU times A minus 1 is equal to PAA minus 1, which is equal to P. So we will do the same calculation by writing LU C1, but instead of being equal to E1, it's equal to the first column in P. So P is given by P1 to Pn. And then this way we'll calculate C1 and etc. LU Cn is equal to Pn. So we have all these systems to solve in order to find A minus 1. In what follows, you have an example where you can practice a little bit if you understood the method or not. Try to do the calculation by yourself and compare it with the results in the document. So we finished this chapter, and then in the next one we'll be talking about the iterative methods. In fact, in this whole chapter, you notice that I'm doing calculations that will lead me to the solution in a direct way. I mean, I'm not calculating iterations to find the solution, to approach the solution in a way that if I perform more iterations, I will be closer to the solution. I'm not constructing a sequence. So they are not iterative methods. They are direct methods because they are giving me one solution, which is the solution. Now, in the second chapter, we'll be talking about iterative methods to solve AX equal B.